So today I'm just going to talk about some of the kind of neat things I learned about PySpark's mllib, which I'm becoming a big fan of the mllib and some of the tools that are in there. Um, there are some rough edges, and as I continue to learn more about it, I kind of go, "Oh, this is cool. I'm going to share this." I will confess that I didn't get as far today as I wanted to in figuring out some of this stuff. I had hoped to talk about cross-validation features in the PySpark ML pipeline. And I can do that. I learned a little bit, but I feel like there's something I'm missing because it's not as cool as I thought it would be. And I also know that Foundry, the Enclave, interfaces with these pipelines, both for PySpark, mllib, and I think sklearn pipelines. I don't know much about that, but they even have like a whole GUI where you can set up and track metrics and things of that nature. And I haven't gotten into playing with that. So I will share my screen. So this is in our training workspace, loading up the notional data. And I've started with the logic liaisons fact table, COVID positive fact table, the notional data version of it that Andrea presented in previous presentations. And I just pulled out some columns here. I have person ID, age at COVID, just an integer, CDM name, BMI, which has some null values in it, an obesity indicator, gender string, pre-COVID history days, and hospitalized. And I'm sort of imagining that we want to predict this hospitalized column from these other variables using like a logistic regression. The first thing I guess to know about PySpark's mllib is that pretty much everything is either what we call a transformer or an estimator, which creates a transformer. And so I kind of tend to think of them as basically the same thing, but there's kind of a distinction. And what a transformer is it's a Python object that can be given a data set and transform it into another data set. So in this case, binarizer is a transformer. And what you do when you specify a transformer is you say, okay, this is a thing that's going to be able to transform a data set that I give it. So I need to tell it what the input column it should look at is and what the output column it should generate it is when it does that transformation. And the threshold here is 365. So what this is going to do, this is a binarizer. So anything that's less than or equal to, I think, 365 is going to be turned into 0, and everything beyond that is going to be turned into 1 in this year history or more column. And then once you've sort of initialized this object, then you can say, okay, would you please transform my selected facts Spark data frame? And it will return basically a new version of that with this additional column on it. So I think I previously run this in the original input. You know, we didn't have that binary column, but now we have this transformed binarized column, which basically is 1 if this is greater than 365 and 0 if it's less than that. The other thing, so I said that these bits and pieces are either transformers or they're estimators. An estimator is something that can give you a transformer, but it first needs to be fit on the data. So let's consider an imputer. In this case, an imputer is something that's going to take, and it's an object that we're going to be able to use to work with data and stuff. So we have to create it, and we say, okay, we tell it what it should look at for its input column, and we should tell it what it's going to need to create as an output column. And then most of these have some additional parameters that you can specify with them. And just so I show this, and we'll probably refer back to this, the API documentation is a little bit, I don't know, it's just a little bit hard for me to read, but it's useful once you sort of get the hang of it. And I usually just find it by like doing PySpark API or PySpark mllib API. And I go to the API one. The guide is good too. And you, well, that took me to 2.3.0. Let's go back up to this one. API docs, programming guides, mllib. API reference. There we go. So this is the API reference. And you notice that it says latest. So this is referring to the latest version of PySpark, but we don't necessarily have the latest version of PySpark. What we have, if I go to the environment and I say review resolve packages, is PySpark 3.2.1, and apparently a Palantir slight modification of it, but that's the main version of PySpark that we're using. So the quick way to get that is just to replace this latest with 3.2.1. And that takes me to the API for that particular version, so it won't show me stuff that's not available to me. And if I look under the mllib header, there's lots of documentation for transformers and estimators, and these are the sort of parent classes for what we're dealing with. But you can also look at each individual thing, and I can look at, for example, that imputer. And what this shows me is that there's an imputer, and you can see sort of the parameters that you can give. So you can say strategy is a parameter, which defaults to mean. Missing value is a parameter, which defaults to not a number. Input calls, which defaults to none. Output calls, which defaults to none. Input call, which defaults to none. Output call, which defaults to none, and this relative error. In this case, I'm using the input call and the output call, but some of these can actually transform multiple columns at once. So I could be like, okay, I need to impute columns X, Y, and Z, and the output columns will be, A, B, and C, or whatever it is. But I'm just going to do this for one. And then they usually give a handy little example where they sort of create a data frame. And it's possible to set parameters directly when you create the object. That's what I really usually do. But you can also just sort of create the object and then call methods to set the parameters. And then down below here, it lists the kind of methods that you can sort of interact with this object with. Not all that useful, to be frank. Most things I end up just setting the parameters and then using. But what is handy is that all the way at the bottom, they have the attributes documentation. So these are the things that you can access not as a parameter, but as an attribute of the object. If you're a Python linguist, you just don't put the parentheses after it. And they also describe what the parameters in the thing are. So for example, if I'm using the imputer and I say, okay, the default strategy is mean, which means I'm going to impute with the mean value of the existing values, what other strategies might there be? The best place to look for that is way down at the bottom, where it says, okay, strategy, if mean, then replace with missing values, the mean. If median, use median. If mode, use mode. And it'll tell me what this relative error thing is about, and so on and so forth. So going back to my code, an imputer, in order to impute with the mean of the existing column, it has to actually compute the mean. So what that means is we have to call its fit method. And so imputer is a estimator, which means that it has a fit method. And when you run the fit method, it returns a transformer, which means it can actually transform one data set into another. So here what we're doing is we're saying, hey, please compute the mean of the BMI column the values that are non-null. That's what the fit method does for this particular thing. That returns a transformer, which we can then say, hey, please transform my data set, which will grab the values from the BMI column, and where they're null, impute them with the computed mean, and the output column is going to be the BMI imputed. So now I have my BMI column, which has values and some nulls, and then I have my BMI imputed column, which has some values, and where there were nulls, now there's the mean of what was there. Okay, any questions about that? So again, the really cool thing I think about this is it's all PySpark, and they do implement a lot of machine learning algorithms. And so now you don't have to be worrying. If you use this stuff, you don't have to worry about whether it's going to fit in memory, right? Like I can run a logistic regression on 500 million rows. And that's pretty cool. When that's what we'll do later on. Okay, so estimators, you can kind of do, estimators have this fit method that returns a transform that has a transform method. Transformers just have the transform method. This fit/transform split allows you to fit on one data set and then transform another data set, or transform multiple data sets, right? So for example, suppose I wanted to say, you know what, I think that I don't know what the BMI values should be here, and so I'm going to impute them. But you know what? I think that my OMOP people are better about assigning BMI values than some of these other CDMs. So maybe I want to get the mean BMI for just the OMOP values and use that for my imputation. To do that, I can first grab out just the data that has the OMOP rows, right? Select filter out where the CDM name is OMOP. And then I'll create an imputer, which is just like I had before, but I'm going to call its fit method, and here I'm just doing it right in line, on that OMOP only facts. So it's fitting, or figuring out the parameters it needs to estimate based on that given data set. That returns a transformer, and then that transform I can use to transform another data set, like the whole data set, to do the imputation. And so now in my output, I again have this, except it's kind of hard to tell, but this is actually a slightly different value than we saw before, because it was fit over just the data set that included the OMOP rows. So then we have, all right, so this is kind of cool. And you can kind of chain these things, right? Like maybe I have a data set, some of my columns I need to binarize, and then some of my columns I need to impute. Maybe I need to binarize and then impute. And you can sort of chain these things onto each other, right? Fit, transform, so on and so forth. And the mllib includes something known as a pipeline that makes this kind of easy to package up. And so you import it as a pipeline. And what you do is you specify a pipeline object, and then you tell it what the stages of the pipeline are. And that is going to be an array or a list of these transformers and or estimators. And the pipeline object itself, so here's my workflow, which I'm calling the result of my pipeline, has a fit method. And what that's going to do is it's going to go through each of these one by one, and if they have a fit method, call those fit methods on the given data. So in this case, it would skip over binarizer, because binarizer doesn't have a fit method. It doesn't need one in order to do, it's just a transformer. But imputer needs to have its fit called in order to create the transformer that will actually translate the data. So once you have these things sort of packaged up in a workflow, a pipeline, you can say, okay, fit on this data, fit all the pieces of the pipeline that need fitting on this data. And then that will return what they call a workflow model, which has a transform. It's sort of like a transformer itself, where I can say, okay, run this data through that fitted pipeline. So this does pretty much the exact same thing as our earlier two examples. I just packaged them up into a pipeline and then called fit and transform on them all at once. BMI imputed and then my binarized column. All right. Many of the machine learning, many of the things in the machine learning package in PySpark work on columns of vectors. And vectors are kind of like a specific data type to the mllib. And to create them, the simplest way to create them is also with a transformer. There's a transformer called vector assembler. And it takes as its parameters the input calls, which is an array of column names. So I'm going to say, okay, I'm going to want to create a vector column out of my BMI column and my age at COVID column. And I want the output column to be called features vec. And I'm going to say handle invalid equals skip. I'm going to go look at the docs for this thing so we can read about this handle invalid. So here's an example of the vector assembler, which is handy if you're just getting started, but I'm going to skip down to the bottom where it just sort of describes what these various parameters do. And this says you can skip, which filters out rows with invalid data, meaning nulls. Error, which is the default, which would basically just say, I found a null, I'm quitting. Or keep, which is to keep the numbers, but put not a number in that vector entry. Because vectors are vectors of numbers, so they can't have nulls per se, but they can have not a numbers, kind of like R does it. So I'm saying skip here. So basically my missing BMI column values won't be included in the output. And then I will say, I call the dot transform on it, and it will create this, zoom stuff's in the way, this features vec column, which is a vector UDT type. That's how you can know it's one of these special vector types, and it usually has sort of a structure kind of feel to it. Now it gets interesting when you want to create a vector, or you want to include in your vector for usage downstream, because lots of these methods use vector input, is if you have a categorical column, because you have to encode your categorical column as a vector. The usual way to do this is to one-hot encode them, right? So for example, suppose that I want to include in my vector input or create a vector to represent the CDM name. There are 3 different CDM names. And so, for example, and in order from most common to least common, they're OMOP, pcornet, and ACT. And the default is to do this from most common to least common. So OMOP would get the vector 100, pcornet would get 010, and ACT would get 001. The other way to do it right is to just sort of say, okay, OMOP is 1, pcornet is 2, and ACT is 3. But that's not really great for machine learning models unless for some reason ACT is 3 times more than OMOP or something like that. But for the most part, if you're just encoding categorical information, one-hot vectors are the way to go. Nevertheless, in the mllib, in order to create these one-hot vectors, you have to start by creating these index numbers and then convert these into one-hot vectors. And in fact, what they do is they give them index numbers starting at 0. So 0 will mean when it's translated into a one-hot vector to put the 1 in the first slot there, and so on and so forth. So there's a transformer, rather an estimator that will do this indexing for us. And it's called a string indexer. You give it the input column that it should read, tell it the output column that it should create, tell it how to handle invalids. I'll say keep. And then what I'll do is I'll say, okay, fit it on the selected facts table. And in this case, the fitting process figures out which one is the most common to least common, so that the most common can be, the first one, and the least common can be the last one. There's also a parameter here. If you were to go look up the string indexer API, you could tell it, instead of ordering by most common to least common, you could tell it to order the levels by alphabetical order or something like that. Once it's been fitted and it sort of, has read the data and figured out its stats, then you can call transform, and that will actually do the transformation into the one-hot vector. I'm sorry, into the index number. So in this case, now I have this CDM name index column, where OMOP is 0, pcornet is 1, and act is 2. That is what we're going to turn into the one-hot vector. There's something kind of cool here to note, which is I'm not showing any nulls here, but the keep instruction for this particular transformer, what it does is it keeps nulls and it puts them in their own special category. So it kind of treats nulls as like the last type. And so if, for example, I had a null over here in my CDM name, it would get index 3. All the nulls would get index 3. If I skip, then they wouldn't be there. So from there, in order to do something with that one, we have to turn it into that one-hot column. And that's this sort of F2 step that I put here. We use another transformer estimator, which is a one-hot encoder. Much like many of the other ones, you tell it what column it should read, what column it should create. And then it takes this cool parameter, which is drop last. So basically, this drop last thing says, if you see a category or an index of 3, in this case, which is our nulls, then it'll drop that. Now, this is kind of neat because suppose OMOP, if we include the nulls as an extra category, OMOP is encoded as 1000, where this index is used if it were a null. When we use drop last, it becomes 100 because we're ignoring what's happening in that last one. Null, however, would be encoded as 0001 because this is what's being used for the null value. When you use the drop last, it becomes 000. So this string indexer and this one-hot encoder are kind of meant to go together, because what it does is it encodes nulls as an entirely 0 vector rather than a one-hot vector, which is a pretty decent way to handle unknown categorical information if you're going to build a machine learning model on it, because it's not really similar to any known other one, right? This will be one off from all the other ones. So this is a handy thing to do back to back. And like most of the other ones, I'm going to fit to figure out what needs to be done, and then I'm going to do a transform to actually do the transform. And now I have this new column, which is also a vector. And it looks a little bit different because they've decided to make this vector output a sparse vector output. There's two different kinds of vectors. and for the most part, you don't have to worry about it. There are dense vectors where they just list all the values. But if you have a vector that's 10,000 things long and most of them are 0, you probably don't want to list 10,000 zeros. So they've encoded as a sparse vector where they say, okay, oops. This is a vector of size 2. The 0th index is 1. All the other indices are 0. So this is just a way to encode a long vector that has mostly zeros in a short space. Any questions about that string indexer to one hot encoder example? Something I skipped over after we created our BMI and age of index thing is scaling these vectors. So if you're going to give a vector to a machine learning model, often you want to normalize these values so that they have like a mean of 0 and a standard deviation of 1. Otherwise, it gets hard to interpret like your feature weights and stuff like that because BMI values are on a smaller scale than ages and so on and so forth. mllib has a standard scaler, which takes an input of a vector column and spits out another vector column, and you can tell it whether it should scale normalize to a standard deviation of 1 and whether it should normalize to a mean of 0, and you can do one or the other or both. And much like all the other pieces, we start with fitting so that it can compute the means and the standard deviations and stuff to do the math. And then we use the transform to take that input and create this new column. And now we get out a normalized vector where each entry is normalized according to the mean and standard deviation, or the first entries are normalized according to the mean and then standard deviation of the first entries. The second entries are normalized according to the mean and standard deviation of second entries, and so on. Okay, so we've got lots of ways to encode data. We can take columns and we can turn them into vectors. We can binarize stuff. We can do feature imputation. We can do one-hot encoding of categorical variables. And we know about this pipeline thing. So rather than doing this all in separate steps and fit, transform, yada, 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 let's actually just build it all into a nice pipeline. And that's what I've done here. So this reads, again, that original data, and I'm building this workflow of a pipeline. And the first thing I'm going to have it do is it's going to do a binarizer to compute my year history or more column. I'll also add an imputer for my BMI column to create a BMI imputed column using the mean imputation strategy. I'm going to take a string indexer to encode the CDM name as an index, and then follow that up with a one-hot encoder that takes that index column and creates the one-hot column. Similarly, I will have a string indexer to encode my gender column into an index column, and then a one-hot encoder to encode that index column into a one-hot column. Now, this is going to be a regular column with zeros and ones. This is going to be a regular column that's just numeric. This is going to be a vector column, and this is going to be a vector column. We're going to want to feed all this information into a machine learning model, so we have to combine it all into one vector. Fortunately, the vector assembler sort of does the right thing. It says, oh, you gave me a vector column and another vector column, and then a numeric column, and then a binary column or whatever. I'm going to stitch them all into one vector, just sort of concatenates values and vectors together to create an output vector called all features. And then after that, the last step, I'm going to take that concatenated features vector, and I'm going to use the standard scaler on it to scale everything to a 0 mean and standard deviation and 1 standard deviation. Now, what's kind of neat about this is that this thing actually, it's kind of like a directed acyclic graph, right? Like this one needs the output of this. This one needs the output of this. This one needs the output of all the previous ones. But this one doesn't need the output of anything, and this one doesn't need the output of anything. So Spark can optimize this and be running things in parallel and doing things, you know, as it does to optimize its execution, which is kind of cool. And then finally, we can fit, which basically says, hey, figure out all this stuff and do what I said to do with it, and then transform it. And the output will be the data set with all these intermediary columns, as well as our final all features scaled vector, which in this case is a dense vector with lots of values in it. And so this is the vector that we can give to one of the machine learning models that takes a vector input in the thing. So from there, I can do a machine learning model, which is a logistic regression. This is much like an estimator, like the other ones that we saw, because it has a fit and it has a transform. This one has sort of different inputs and output column parameter names. So in this case, it's not input call, it's features call, basically saying, hey, read the features from there, which should be a vector column. It's got a label call, which says, hey, this is the thing we're trying to predict. And then it's got a prediction column, which is basically saying, instead of output column, is saying, put your predictions in this new column. And by the way, this one also takes a parameter, write the actual probability values into this particular column. And now the fit is much more like a machine learning fit, where it actually figures out the logistic regression parameters, and then we transform to make the actual prediction. And I have my two output predictions here. I guess I also have a raw prediction. I don't know where that came from. There's probably a parameter I can set for that. This is the predicted binary labels, and then these are the probability 0, probability 1 values, which are encoded as vectors as well in the output. Okay. So one of the tricks with machine learning, many of you probably know this, is that you don't necessarily want to evaluate your model on the data that you trained it on, right? So ideally, what I would do is I'd say, okay, let's split this data into a training set and then a validation set. So I can fit it on the training set, and then I can run the validation on the validation set. Right? And then I can evaluate how it did. The thing is, it's not just the logistic regression that we're fitting on the training set as opposed to the entire data set. Because the input here, these all features scaled, these were built on the entire data set, right? And so if I'm training my logistic regression model on the training data set, but the imputation was done on all the data set, then I'm kind of cheating too, right? Because I have information leakage from the entire data set, including what I'm validating on, into what's going in the fitting. So what we really should do is we should be splitting our training and validation sets up way at the beginning, and then using all the feature generation stuff to fit the imputers and all that kind of thing, as well as the model. And then on the other one, we use the same imputers and everything on the validation data. Essentially, what I'm saying in here is that we should be adding to our existing pipeline, which has all this feature generation stuff, the logistic regression model itself. So now if I were to say, is workflow.fit, training data or whatever it may be, then that does the imputation based on the mean of the training data. It does the one-hot encoding based on the values that are available in the training data. It does the scaling based on the training data. So we're not cheating by taking a peek at any other data that we shouldn't have, and we're fitting our logistic regression model on that training data. Then later on, I could say workflow fitted dot transform validation data. And then I can sort of see how it did. One of the things I didn't exactly get to is it can be handy. I've covered this in other EUG presentations. It can be handy to return a fitted pipeline. So maybe I would say like that. And you're like, okay, I have this fitted pipeline. I want to use it in my code workbook, but I want to use it on one data set here and another data set there and do this other thing with it. So rather than returning a data frame, I'd like to return this fitted pipeline. And you can actually do that. I think you do. Well, I'd have to look it up. It's in the documentation, but there's a way to basically convert this into a Foundry thing that can be exported so that it can be read into other transforms, and then you could do stuff with the whole pipeline. I think it's like from Foundry ML import model stage. I think you have to do a little deconstructing of this. And so you're going to be like return model stage X for stages in workflow fitted stages or something like that. Basically, you have to convert, these are called stages, and you have to sort of pack them into a Foundry enclave thing, and then those get packed into a list inside of a model enclave thing. But in any case, it's just a wrapper for what we've already done. And I probably don't have the syntax right there, so I'm going to delete it. Okay. So what I mentioned about, the right thing to do would be to do some training data and then to evaluate based on some validation data. One way to do that is to do cross-validation. I assume you all are somewhat familiar with cross-validation. But this picture here sort of gets at the thing. You basically take your data set and you split it up into chunks. And then in iterations, you use one chunk as your validation data and the rest as your training data. And then you do it again, but now the second chunk is your validation data and the rest is your training data. And in the third iteration, and so on and so forth. This lets all of your data be sort of included in the training part at some point and the validation part at some point. So it's an overall good view of how the model works on all the data, reducing the chance that you might have just picked some bad data for your training or your validation by unlucky happenstance. And then what you get is sort of like a bunch of different models with a bunch of different quality metrics, and you can pick the best one. Or you use a single model, you do it a bunch of these times, and you average the quality metrics to get at your model's quality metric. That's the way it works. So mllib does have a cross-validator thing, and I'm not super impressed with it so far, but I feel like I'm missing something. It does do cool stuff for you, though. And here's how it works. For one thing, it helps if you're able to have a variable that refers to one of the stages in your pipeline. And there are a couple ways to do that. You can sort of like have your pipeline and then figure out the API to get at one of the things inside of it. Or you could just say, imputer equals that, and then put imputer there. And then later on, I have this imputer thing to work with. And this is handy for this cross-validation business. So whichever way you do it, what the mllib pipeline has is a way to specify a grid search over parameters. And the API of it is a little bit weird. There's examples in the docs. But you create this grid builder object, and then you add to it parameters that you'd like to iterate over. And so I'm going to say, you know what? I want to try for my BMI imputer, which is this thing up here. I want to try its strategy parameter. I'm going to try mean and median and mode. Similarly, I have a handle on my logistic regression, and that has a reg param, which defaults to, I think, 0.05. So I'm just sort of letting it be 0.05 here. But I can try different values of the regularization parameter for that part of the pipeline. And it also has an elastic net parameter for regularization, and I'm going to try values 0, 0.5, and 1. I think the reason that you need to have a handle on the actual object itself is so that this param grid builder can say like, oh, I'm going to reach into this object and I'm going to muck about with its strategy parameter, and I'm going to set it to mean, and then I'm going to set it to median, and then I'm going to set it to mode. And then you call build on it. And what it returns is a list of all the combinations of parameter settings that you can then use in the cross-validation step. And what the cross-validation step will do is it will run the whole thing with every combination of parameter settings using some evaluation metric, and it'll pick the best combination of parameter settings that maximizes your evaluation metric, and then use that model. So it sort of does the whole business of iterating all the different parameter values, running cross-validation on them to figure out which settings are the best on held out data sets, and then picks the best one for you. In order to do that, you have to create, and this is where it starts to get kind of weird, and we're outside of the imputer transformer stuff that we started with, but you have to create a evaluator. This is part of the mllib's API. It works sort of like a transformer in that I tell it what the raw prediction column it should be using is. And now I suspect that's probably not right because my input, it created a raw prediction column. Anyway, what the label call is, what I'm trying to evaluate, and then the metric that I want to use to do the evaluation. In this case, I'm going to use AUROC. From there, you can create a cross validator where you tell it what the thing you want to have fitted and transformed is, and that's my pipeline, how many folds to use, what parameters you want to iterate over to figure out which settings of the parameters are best, and then what you want to use to evaluate that, each setting of the parameters to figure it out. After that, the cross-validator has a fit. And so you can say, hey, do your whole thing on this data set, try all these parameters, do the fitting, do the translation, evaluate, figure out which one's best, and it will return the best. Well, it'll return a transformer which contains the best performing model inside of that, the best performing pipeline inside of that. And so then you can use that transformer to actually do your prediction. And so now in my output, I again have my HOSProb and HOSPredicted values, but these are the result of the best settings from the parameters that were tested across all the cross-validation runs according to AUROC. What I'm not super happy with is, if you're doing cross-validation, usually you want to know stuff like, okay, I'm evaluating each combination here according to AUROC. What was the AUROC for the mean 0.5, 1 combination? What was the AUROC for the mode 0.5, 0.5 combination? And it's not super easy to get that stuff out. I think that's what this does. Average metrics basically gives you the average, but it just gives you a list, and it's not immediately clear which combination is which output, but I can run it and see. And then you can also get out the best model, which is the best actual version of the pipeline after it's been fitted, not wrapped up in the cross-validator thingamajigger. And then from there, you can reach in and try and get out the last stage, which is the logistic regression, and maybe say, okay, what was the best, what was the settings for this optimal logistic regression that you found or something. But overall, I find this part of the API is really confusing, and I haven't really wrapped my head around it. And in fact, I'll let this run and we can see the printouts, but they're not all that useful. Anyway, so that is, intro to PySpark ML pipelines.
Wow, thanks for a lot of ground you covered today. Do you have to have a set of parameters, or can it just do k-fold cross-validation just a single model?
I think I did do, I think you can just have, I want to say it requires this estimator param maps thing, but I think you can create like an empty param grid.
Okay, or just put one parameter in there or something.
Yeah, or yeah, put like one combination of parameters or something. I think it does require this. It also requires the evaluator, and it was confusing because the examples I found online just used binary classification evaluator without any inputs, but I was using non-standard label calls and prediction calls, so I had to like create it separately and set the parameters.
Well, you did a lot of figuring out of how to actually use the API. So this workbook could be very useful.
The feature generation stuff is quite nice.
Do all the actual machine learning methods require vectors as input, which seems like
no, not all of them.
Oh, okay.
The ones that tend to be sort of feature-based will, like logistic regression and stuff, but like clustering might just include an input column that's, document name and label name if you're doing topic modeling or something. So no, they don't all have to take input vector inputs, but the kinds of methods that tend to take vectors of feature inputs probably are going to be set up to do work that way.
It seems quite extensive. I haven't looked through it before, but it does everything that's in, sklearn and.
Yeah, I mean, there's gradient boosted trees, random forests, logistic regression, linear regression, lasso, isotonic regression, recommendation systems. So if you want to build something like Amazon, people who are interested in this might also be interested in that. You can use the alternating least squares method.
So what's the difference between mllib data frame versus RDD based?
Oh, I don't know the answer to that well. I know that RDDs are this sort of like generic container for Spark data, and Spark data frames are a particular kind of those. And so I think that the data frame based one is now the default. They're going to deprecate the RDD one. But this is an older one that I think is just built against more generic-y kind of data. Still
Okay.
probably mostly we're going to data frames, but you have to go through the RDD API, which I don't really know much about.
All right. Now we just have to go try this ourselves, don't we?
Go build models on 12 million patients. Billions of rows.
Yeah, how obviously the benefit of this is it can work on large data sets, but it's probably slower than if you could bring it all into memory and just use.
Yeah. If we had terabyte machines, that probably would be faster ultimately than having to shuffle things over the network and deal with all that kind of thing.
Well, great overview of that.
Okay, well, thank you all for coming and listening to me recapitulate what I learned this week.
Well, thanks for sharing it, and more importantly, documenting it in a working code book so we can refer to it.
Yep, I'll put this over in the users group folders and index it as normal. So,
Great.
all right, take care, y'all.
Thanks, Sean. Bye.